Alright, hello and welcome. Today is Friday, May 8th. May 8th, I was about to say May 7th. May 8th. We are nearing the end of our school year. I see that a lot of you have signed up for your Seneca Learning account, but still missing a handful, probably like 10 people or 20, 15 people. If you haven't, please check the posting for yesterday on Canvas 5.7. So you should be making your Seneca Learning account and then log in and start your actual assignment. Are we still doing nothing else? We're not doing anything else besides the Seneca Learning. Remember I said yesterday that no new assignments will be posted. That's pretty much the end of physics. I've opened up Unit 11 on the website, so you can download the PowerPoint slides if you want. The PowerPoint slides actually have a lot more information than we are going to learn this year. We're going to cut the unit short because we're kind of out of time. And so over the next few days, I'll try to go over some of the slides, at least the ones that are conceptually important, and so and then skip on all the other topics that I don't think will be necessary, at least this year. All right. So please, I'm only seeing, although a lot of people have signed up, only a few have actually started doing the work. So do not wait until the last day. Something always goes wrong on the last day. So get started. Get started as soon as possible, really. Okay. So let us begin by talking about magnetism. Let's pull up. So here's PowerPoint slide. This is the first PowerPoint, Magnetism Part 1. Again, we're not gonna learn everything this year. Well, only a few essential slides. Of course, some basics from elementary school, middle school. I don't know when was the last time you guys played with magnets. But magnets have poles. It's similar to electric charges, but they're not the same thing. I mean, they behave like electric charges. Remember, electric charges can be plus or minus, and then opposites attract, like charges repel. Similarly, the rule for magnetism is the same, but instead of charges, we have poles. They're related to each other, but they're not the same thing. So the magnetic force is technically different from the electrostatic force, but they are intertwined. It's almost like buy one get one free. So when you have two norths, they repel. Two souths, they repel. But if you have a north and a south, they will attract. So these are two different magnets. That's the law of poles. The law of poles is just an extension of the law of attraction for electric charges. So let's take a look using a simulator. Let me pull up my simulator view. Here's my simulator. So this thing is a compass, right? And I have a magnet. Now typically you have a south pole and a north pole. So we have a compass, and the compass generally, if you're not close to any external or like strong magnets, the compass will show you which way is north, at least the geographic north, and we'll talk about that today. But here's a bar magnet. When you bring a compass near a bar magnet, the compass actually changes its direction. Whoa, look. Right, if I'm over here, the red points towards the S, which is the south pole. And then if I'm over here, the white part points towards the north, which is the north pole of this magnet, at least. Not the so you have to separate geographical north and magnetic north. So when I am here in the middle, it does something interesting. Okay. This is an exercise we've done before, except with electricity we didn't use a compass. right? With electrostatics, we had a big giant charge. In this case, we've replaced that charge with a bar magnet. We used a small test charge to map the electric field around our charge. So similarly, what I'm doing is mapping the magnetic field around a magnet using a compass. Whoa. So by placing it at different spots, I'm going to keep drawing the direction of the compass at each location in space. And what we end up getting is the actual field. So let me draw the field. Boom, there's the field. So, you can see how it's similar to the electric field, but this is the magnetic field. The magnetic field shows you the direction of a compass, really, at that location in space. It shows you the direction of the field. Okay? It turns out that a compass is actually a tiny little magnet, right? We used a positive tiny little test charge to map the electric field. So the electric force that is applied on the tiny little test charge is the direction of the electric field. Similarly, this is the force that the compass is experiencing based on this bar magnet that we have. So a compass is just a tiny little magnet, and you see how the red, which is the north of the compass, points towards the south because the north pole of the compass is attracted to the south pole of this bar magnet. North and south attract. And if I move it to the other side, whoa. So the south end of the compass is now attracted to the north side of our bar magnet. Right? All right. And here in the middle, see how it aligns. So the direction of the magnetic field comes out. If you think about actual directions, red being the forward direction, so it comes out of the north side and then it loops around and then it goes back into the south side, Okay, but what's interesting is that the magnetic field doesn't just exist outside in space, it also exists inside of the magnet. And so I can show you the inside of the magnet. Boom. And inside of the magnet, it's actually in the opposite direction. So on the outside of the magnet, the lines go from the north, it curls around, and then goes into the south, but it's a loop, it's a circle, meaning as you go into the south pole of a magnet, you'll go through the body of the magnet, and on the inside you go from south to north, and then you come back out again. So on the outside it's north to south, on the inside it's south to north, and so we loop around. PowerPoint. Oops. Where's my PowerPoint? There it is. All right. So when I break a magnet, I'm sure you've done this. If you have magnets and you dropped one, typically they're made of ceramics and some very fragile, light material, and they shatter. So if you drop a bar magnet and break it in half, you can't actually separate the south and the north pole. What you end up doing is you create two miniature magnets. So at the break point, okay, you will create a new north pole and a new south pole. Okay, so the south pole, of course, is opposite to the old north, and the north pole is opposite to the old south. And if you continuously break, if you keep snapping these in halves, you're going to get smaller and smaller magnets, but these poles, north and south, will always come in pairs. Okay? So classically, in the classical physics world, these poles, magnetic poles, come in pairs. So if you have a south pole, you're going to have a north pole automatically. There's no way around it. Unlike electric charges, you can actually have singular charges, right? You can have a positive charge by itself. You can have a negative charge by itself. You don't have to have both. But with magnets, you get both. In the current New Age physics, apparently it is theoretically possible to separate and encapsulate a magnetic monopole inside these crystals and some very high level physics stuff that we can't really discuss. But we're going to leave that stuff out. In the classical physics world, normal magnets come in pairs. Pairs of poles, at least. All right, now why do these poles... Oh, actually, I should say, why do you get new north poles and new south poles? Why can't we just capture the north and the south? Well, again, let's take a look at the magnetic field inside of a magnet. This might explain why that happens. So inside the magnet, remember, the field goes from south to north. So let's draw a magnet. So here's my magnet. Here's the south pole, here's the north pole. Of course, the field goes out of the north and then loops around and goes into the south in both directions. Okay, but on the inside of the magnet, the field, it's a loop. So in order to finish this loop, kind of like circuits, we're going to complete our circuit by completing the loop. It's a closed loop. Whoa. Okay. And so on the inside, you can see how this direction is towards the right with my picture here. So if I break it in half and snap it in half, notice how this side, the left side would look like this. Here, let me see. Oh, actually, that's too complex. Let's make an easier break. There we go. So let's break it like this. Looks like the Harry Potter thing. That little scar he has on his forehead. So here's the left side. The left side looks like this now. Or a DNA nucleotide. Any biology fans in here? This looks like a DNA nucleotide. So we know that this was the south. And after breaking it, we have magnetic fields that, oops, let's use a different color, that point to the right. Okay, and you can see how if I compare it to the original picture had a south here, had a north here, has arrows going to the right. Okay, whichever way these arrows come out is essentially the North Pole. And so that's why, like, anytime you break a magnet, okay, the inside didn't really change. So the fact that the arrows are coming out on that side means that that side essentially is the North Pole. The North Pole isn't a physical, entity. It's not like a thing that you can see. There's no little, what's the classical North Pole? Usually there's like an actual pole that's like striped. There's no pole. It's just it's a location in space where the magnetic field lines are coming out. There's no physical characteristic that actually tells you where the North Pole is, but you can feel it. So even though you can't see it, you can still feel the force. And so if you were to put another magnet here and happen to be on the north side facing in, you're going to get repelled away. And so even though we can't see these things, we can feel their effects, we can feel the force. And by measuring the force, we conclude that it must be a North Pole. Right. Now for the Earth. Let's see. Earth. Oh, whoops. I'm going to skip all this. This is, from the actually. I guess we'll talk about it. Where does magnetism come from? Magnetism is linked to the electrostatic forces or charges. So from electrostatics, we have particles like electrons. So imagine this being an electron. The electrons have what's known as a spin state. Now, is the electron actually spinning? You can't really see it, obviously, but for whatever it's worth, we've characterized this quality of the electron to be a spin state. So you may have, if you took chemistry, you may have learned that there's a spin up and a spin down. So let's say that this is a spin up, whatever that means. I'll use spin in quotes. Spin up. And this would be a spin down. Okay, so if we imagine the electron to be like a ball, right, a particle ball, then the spin characteristic can be seen as a ball rotating around. Okay. What we do is we actually use our left hand to figure out which way the spin is, where the thumb points. So if you, let me see if I can draw my left hand. So I have to draw it so that, imagine like grabbing a pencil. Let's see, here's my thumb. And then here are my fingers, and I'm going to curl my fingers. Is that good enough? What's wrong with my fingers? Oh man. It's like a thumbs up. You got to give yourself a thumbs up. Or this is your left hand. We're using the left hand because it's a negative charge. The electron. Alright, looks like the Facebook thumbs up. I think this is my hand. You can imagine looking at your left hand, just curl your fingers inwards with your thumb sticking up. This is the left hand. Okay. So the thumb is pointing in the direction of the spin. And the curl of your fingers, viewed from above, from a helicopter point of view, is showing you the actual rotation. So notice how if the thumb is upwards, your fingers are curled this way. The green is the curl of your fingers, and that gives you the rotation. So the direction of the spin is called up, but the way it's rotating is this way. So if you look at it from the top, it is going in a clockwise fashion. Where we're using our left hand because it's negative. Typically with positive charges, you would use your right hand. So use left hand for negative charges. Left. Right hand for positive charges. Okay, so with a spin down electron, you would actually have your thumb point. You'd give yourself a thumbs down, thumb pointing down. Basically, it would be spinning in the other direction. Yeah. And so the idea is that these electrons are spinning around inside of your magnet, and so each region, it's kind of like red states and blue states almost. Each region inside, or called domains, have a preferred direction of spin. So the inhabitants of each region have like a direction of spin, but generally they point towards the same direction. And the net vector, by adding all of these vectors together, you get the sum, which is of an arrow that points to the right. The y components kind of cancel out, because it turns out, if you have a y component here, let's use a different color. Right? If this arrow were to point upwards to the right, this y component might get canceled out by the y component of another region. So essentially, for the most part, the y components cancel out, leaving you with only x components that point in the same direction. Right? Okay, so the spinning of electrons or spinning of charges is what generates the magnetic field. So these spinning electrons have what's known as a magnetic moment. So imagine these electrons being little tiny magnets. You could say it's like the angular momentum vector. If you want to learn about angular momentum, consider taking AP Physics 1 next year. All right, back to the PowerPoint. So in a permanent magnet, the magnetic field comes from the electron motion inside of atoms, or inside these domains. The domain is like the region I was talking about. A zone, a city inside of your magnet, where all the people, all the inhabitants, all the electrons have a net direction of spin. Right? We can't, even though we have spin up and spin down, the electrons actually can be rotated. So you can have it so that the electrons are rotated around. So even though it's up spin, but you force it to rotate so it's at an angle. So you could do that. We can use magnetic fields to rotate electrons. Electrons technically exist in all orientations. It's not just spin up. If you just leave the electron alone, it's actually everything. It's just that if you actually try to measure it, 50% of the time it'll come up spin up, and 50% of the time it'll come up spin down. But in nature, you can imagine it being like a coin. So imagine this being a quarter or something. You ever flicked a quarter on a table? If you apply your force, boom, this way, the quarter starts to spin around like this. Okay. So imagine, naturally the quarter is always spinning, so you don't know if it's heads or tails. However, if you try to measure if it's something heads or tails, you actually have to kind of stop the quarter, press down on it so that it falls onto the table. Okay. And so, but whenever you make those measurements, notice how half the time your quarter will say that it's heads, and the other time the quarter will say that it's tails. So similarly, electrons actually spin in all weird directions. It's always in, it's doing all sorts of weird stuff. But if you were to actually measure it, it'll take a shape, or take a conformation, or take a side and force to be spin up or spin down. Okay. And it is this it is this magnetic moment stuff that kind of forces your chemistry students know about your electron orbitals, how you have only two, and inside your orbitals you have up and down only. You can't have up and down. So now you kind of get why that is the case. It's that, imagine if you have up and up electrons. These electrons are like little tiny magnets, and these magnets would kind of repel each other. In a I drew all this stuff and I forgot to show it. Here's my quarter, and my quarter is spinning around, and so when I force it down, it turns heads or tails. Oh, 50%. Of course, you have to do it many times. You can't just do it once or twice. You need to do it thousands of times. All right. And there's another way to produce magnetism through electricity, and that's something we'll talk about later. So I showed you this with the simulator where you take a compass, move it around, it shows you the magnetic field lines. And on the inside, remember on the inside it goes south to north, on the outside it goes north to south. North to south. Notice how on the bottom it curls. So it curls around and then goes back in. Okay? Of course, the further out you are, the weaker the magnetic field is. Just like electricity or electrostatics. All right, let's get to it. Finally, I'm sure you've heard how the Earth is a magnet, but the magnet is actually tilted, so it's not really straight. And the tilt is enough to matter, but it turns out that the actual geographic North Pole, so you imagine where Santa Claus is, the geographic North Pole here is actually the south magnetic pole. So if the Earth is a magnet, then it's an upside down magnet. Okay. Now, why is the North Pole the south magnetic pole, and why is the South Pole the north magnetic pole, etc.? Well, actually, the poles can shift, meaning one day in the future, the magnetic South Pole will realign. It'll actually turn all the way around 180 degrees and become the North Pole again. So it can, flip. But it only happens, hundreds of thousands of years after, in the future. But it means that it has happened in the past as well. So why does your compass point north if the North Pole is actually the South Pole? Okay, so this picture is trying to show you that the compass is on the surface on the planet, and the magnet is actually internal. It's on the inside. Okay, so when you're on the ground using a compass, that's just like having a compass on the outside of a bar magnet, so kind of like this. So when you're walking on the surface, you're actually outside, and notice what happens on the outside. On the outside, the magnetic field line points from the north magnetic pole towards the south magnetic pole. So if I take a look at Earth again, so the North Pole is actually down here at the bottom. The lines come out of the North Pole, it loops around, and then it goes back into the south. So on the outside, okay, the compass, which is a tiny little magnet, will align itself such that it is pointing towards the south because it's being attracted towards the South Pole. So if I go back to my simulator, here's my simulator, right? So notice how, oh gosh, can I rotate this? No, I can't. I can't rotate the bar magnet. No. But anyway, we'll just look at the Earth sideways. So this north is actually the South Pole of the Earth. So the magnetic field comes out of the north magnetic pole and then goes towards the south. So when I put a compass here on the surface in the middle, of course it's going to, the red, which is the north pole of the compass, will point towards the south pole of the bar magnet. If I'm over here, it'll point directly towards it. And so that's why it points towards the north. It's actually pointing towards, it's being attracted towards the south magnetic pole. So someday in the future, your compass will point the other way when the magnetic poles of the Earth shifts. Now, where does the Earth get its magnetic poles? Well, based on the fact that magnetism itself comes from spinning and rotating charges, okay, there must be charges that are spinning and rotating inside of the Earth. So on the inside of the Earth, we have magma and all sorts of stuff that is super hot. When when you heat up fire, you get plasma. And so this molten core must be spinning or rotating. The fluid inside must be spinning or rotating. At least the charges must be spinning and rotating and creating the magnetic field in the first place. And it is this field that acts like a force field. It protects us. It's a shield, a bubble. Okay, and without this force field, we wouldn't be alive. Really. Like the sun is always, shooting all these high, energy particles towards us. Anytime there's like a solar flare and other things, we get a burst of particles that um, shower the Earth. However, the magnetic field acts as a force field, like a bubble, in that whenever charged particles come towards the Earth, um, the charged particle experiences a magnetic force, and the magnetic force pushes the particle away. So instead of going into the Earth, it'll get pushed away and go a different way towards, towards some other part of space. Unfortunately, Mars does not have a very strong magnetic field, and so whenever these particles come, it would push away all of the atmosphere. So that's why the Martian atmosphere is very thin. There is some carbon dioxide there, but it's very thin. It is based on all of the findings and based on all the evidence. We can model Mars, the primordial Mars before it died. The Mars before it died was, probably similar to Earth in that it did have an atmosphere, did have some sort of magnetic field that kept the atmosphere, but somehow it lost the magnetic field. So the inside of the inside core just, stopped working, or it could be that it was weak to begin with, and it was just it deteriorated over time. And once the force field is gone, then the gas particles, the atmosphere, which is just a bunch of gas particles, would get blown away, and now you have nothing. And if there's no atmosphere, then trees and stuff can't grow, so it's just a rock, right? So if it had water, all of the water dried out by now. Now, how do we know if it had water? Well, based on the fact that water causes erosion, and if you see a river that is dried up, you'll see that there's a remnant. The river would cause erosion along the Earth itself, causing an indentation, and these indentations on Mars tells us that there must have been water in the past. All right, I think that's good enough. Please continue with your Seneca learning. You can download these PowerPoints if you want to learn more. Again, I'm not covering all the information. There's no mastering physics. There's no other labs. There's nothing else. Finish up your Seneca learning and you'll be done with physics in no time. But I'll continue to bring up all these other extra stuff just for fun, just so you have a full understanding of what it is that you're learning, so that you understand how things work. Thanks for tuning in. I'll see you next time.